Okay, one element of last lesson was we discussed the difference between descriptive and inferential statistics. Just as a reminder from last class, descriptive statistics are used to organize or summarize data, whereas in this particular lesson, when we talk about inferential statistics, we're trying to draw meaningful conclusions or interpret our results. So here we go. So just to go over some of the learning objectives, we're going to explain how researchers use inferential statistics to evaluate sample data. We're going to distinguish between the null and the research hypothesis. We're going to talk about probability as it relates to statistical inference. We're going to talk about t-tests. We're going to talk about one-tail versus two-tail tests. We're going to talk about ANOVA or F-tests and systematic versus error variance. And we're going to talk about type 1 and type 2 errors, what factors drive type 2 errors, reasons why a person might get non-significant results, the role of power, and various criterion for selecting an appropriate test. All right. So, as I said, inferential statistics allow us to draw meaningful conclusions about a population based on a sample. Now, we talked about sampling a few times, but most pronounced in lecture 7. Now, inferential statistics are the counterpart to descriptive statistics. They're used hand in hand. Now, what is a population? You may recall from an earlier lesson, a population, you're looking at all individuals of interest, whereas a sample is a subset of the population, or some but not all of the participants of interest. Now, I will note that it's very rare that a researcher has access to the full population. So it's very, very important to have a representative sample, as we discussed earlier, and have adequate sample size in order to draw meaningful conclusions about the population. So what do inferential statistics allow us to do? It allows us to make inferences about true differences in a population based on a sample. It also allows us to determine the likelihood that the difference between the averages reflects random error rather than real differences. So you may recall earlier in the semester, we said that every outcome is a combination of true score plus error, real differences plus error. Now, we want to minimize the amount of error variance we have in our data set, but we recognize that there's always some level of error variance. Okay, now, if you hold all of the extraneous variables or confounds constant or use randomization, as we talked about in lecture 1 and lecture 8, then if we have meaningful differences between the means or the averages, we can say that those differences between the groups is due to our manipulation. All right. Now, we want to talk about null hypothesis testing. When you hear the word null, think null and void, nothing doing. So the null hypothesis states that there are no significant differences between the groups. And if there are differences between the groups, it's due to error. If that is the case, if the null hypothesis is true, we would find that our independent variable had no meaningful impact or no meaningful effect. The alternative hypothesis, also known as the research hypothesis, suggests that there are real differences between the groups, or there are statistically significant differences between the groups, and they're due to our manipulation. So the null hypothesis says nothing doing, no differences between the groups. Population means are equal. If there is a difference, it's due to error. Whereas the research hypothesis says there are real, true, meaningful differences between the groups, and it's due to our manipulation. Now, in research studies, we start with null hypothesis testing, right? So why do we assume the null is true? Why do we start with that assumption and we have to come to reject the null? Well, the reason is if we go back to the previous slide, we said the null hypothesis says that there are no differences between the groups. So we can compare differences from 0, right? Because it's clear. If you're saying there are no differences between the groups, the difference should be 0. Whereas if we started with the research hypothesis or the alternative hypothesis that states that there are differences between the groups, that is not precise, because if we're starting with the assumption that there are differences, it could be any number other than 0, so you can't do a meaningful comparison. So that is the reason why we start with the null hypothesis, because if we say the mean 1, which is mu1, is equal to mu2, these averages are the same, well, we can compare differences from that. All right. Now, when we talk about statistical significance or statistically significant differences between the groups, when we use that language, we're saying that the likelihood that this outcome occurred due to error or chance is very low. And when the likelihood of getting an outcome is due to error or chances less than 0.05, we generally reject the null hypothesis. Now, in null hypothesis testing, we start with the assumption that the null is true, but all researchers, our goal is to reject the null. That only occurs when the probability that this occurred due to chance or errors less than 0.05. And in some cases, we might have a more stringent alpha, which we'll talk about a little bit later. Now, p-value or probability. P-value or probability is the actual likelihood that this outcome could have occurred by chance. So, again, we compare the p-value with the pre-established criterion, which is our alpha. Now, the standard alpha level is 0.05. So science generally allows up to 5% error in a study. So if the likelihood, the observed likelihood, was 0.05 or less, we reject the null. So that's what the p-value is. So you look at the p-value. If it's 0.05 or less, you reject the null. Now, you can have more stringent alphas where it's 0.01 or 0.001. A 0.01 alpha is before you do the study, you're saying you're only willing to allow up to 1% error. And 0.001 is you're saying you're only allowing up to 0.1% error. So there are times in research that you want to use a more stringent alpha, things like drug studies, when the risk of releasing a drug is great or great enough that you don't want to cause harm, you would do 0.001. But in science, the standard is 0.05. All right, so, but the distinction, and I want to hammer this home, the distinction between the alpha and the p-value is the alpha is established before the study. When your research team is designing, you're like, well, what alpha level am I willing to accept? And then the p-value happens after you're doing your statistical analysis. Now, if you're working with SPSS, which is a statistical software program, they don't do p-value. They have something in the place of probability called SIG, S-I-G, which is level of significance, which is the same as p-value. So don't be alarmed when you're using SPSS if it looks different. Now, let's say we wanted to look at a research study and we wanted to determine whether your friend had clairvoyance, whether they had ESP, right? So you could give them 5 symbols. You could have 10 cards, 5 symbols that recycle twice. And you could ask your friend to correctly guess the symbols on the card. Now, I want to ask you a question. How many symbols would you feel comfortable that with them getting correct before you say, okay, maybe they can read your mind, right? So would you need all 10 to be correct? Probably not. Most people wouldn't. Would you go as low as 2? Probably not, right? Because if you did 2, they could guess one shape 10 times and hit that marker. So you want to test the null hypothesis. So you could easily get 2 correct, right? Now, what if they got 3 correct? Would that be good enough? How about 5? How about 7? So in this scenario, you set the alpha at 0.05. Now, what you find is that in this scenario, you might need 5 or 7 of these correct to reject the null, depending on your alpha. So again, your sampling distribution is number, based on an assumption that a null is correct, you would guess that they could get 2 correct without even trying. Now, we said 5 or 7. So what if you had them increase the number of trials from 10 to 100? Would we need 50 or 70? Believe it or not, the answer is no. They could get 20 correct by chance just by saying the same symbol. But because we increase sample size, it has sensitivity to smaller differences. So they would need to only get 30 questions correct in order to reject the null. So that's fascinating. 5 or 7 drops all the way down to 30%, or or that would drop it below the alpha. Now, I also want to talk about t-test and ANOVA. So there are a lot of statistical tests out there, and the common ones you're going to see in an undergraduate curriculum, if you're comparing means, are t-test and ANOVA. So the t-test is generally used when you're comparing 2 group averages. So the t-test is used for interval and ratio data, but it has to be 2 groups. Now, the ANOVA, also known as the F-test, is used when you have 3 or more groups in a single independent variable, or if you have a factorial design that would have 4 groups, right? The smallest factorial design we said in lecture 10 was 2 by 2, so that would have 4 groups. Long story short, the F-test or ANOVA is used when you have 3 group means or greater. Now let's look at the t-value. The t-value is a ratio between 2 aspects of data, group differences, comparing the means and seeing if there are average differences. That's your numerator. And then the denominator is your within groups variability. Now the denominator in all of these formulas measures error. Remember that. The within groups variability in the t-test, as well as in the ANOVA, measures error variance. So when we talk about group differences or between group differences, if the null is correct, there should be no difference between the means, right? And what we find is as the mean differences increase, so does the t-value. So the t-value increases when the group differences increases. Whereas within groups variability, that refers to variability around the mean, that refers to error, right? So the smaller the within groups variability, the smaller the error, the larger the t-value. All right. And this is just putting it back together. Now, when we talk about inferential statistics, one of the common things you're going to have to learn about is something called degrees of freedom. And that's the number of observations that are free to vary in a group. So let's say I had a group of 5. How many degrees of freedom would there be? Well, in a single group, it's n minus 1. So there would be 4 degrees of freedom. But think about it logically. The definition is the number of observations that are free to vary from a constant. So if we picked one member of that group, how many individuals are not that member? If the group started with 5, one member is the constant, then there are 4 people that differ from that individual. Now with the t-test, you have 2 groups. So each group is going to have its own degrees of freedom. So in an independent samples t-test, the degrees of freedom are as follows: n1 plus n2 minus 2. So if both groups had 5, right, each group's degrees of freedom would be 4, but you have 2 groups. 4 times 2 is 8. Now you get there with the formula listed on the screen as well by saying 5 plus 5 would be 10. 10 minus 2 gets you to 8. Now, when you're using statistics by hand and you go to the back of the book, there's something called a critical value. A critical value is a score that needs to be met or exceeded to reject the null. And it always depends on several factors. For example, number of degrees of freedom is going to affect the critical value. Whether you have a one-tailed test or a two-tailed test is going to affect the critical value. Your alpha that you set is going to affect the critical value. So you have to be mindful that that's the magical number. That's the threshold that needs to be met to be so far in the extreme of the bell curve that you reject the null hypothesis. Now, there are one-tailed tests and there are two-tailed tests. A one-tailed test is referred to as a directional test. And what that means is that the researcher has a specific hypothesis about how the outcome should occur. For example, if you were creating a drug to reduce depression, you only want to let that drug on the market if it reduces depression. What if it increases depression? You don't want that on the market, right? It creates more problems than it's worth. So a one-tailed test says, hey, I want this only to decrease depression. So you already start with a prediction about how the result should be. Now, a two-tailed test is also known as a non-directional test. And this is oftentimes used when a researcher does not know whether the manipulation is going to increase or decrease the average, the score. So when you're not sure, you say non-directional test. Now, what's interesting is that in a one-tailed test, your 5% error goes on one side of the distribution. Whereas when you have a two-tailed test, if you had an alpha of 0.05, your 5% is split between the two tails. And that has ramifications. So what we typically see is that in a one-tailed test, the critical value is always smaller than a two-tailed test of the same alpha. So let's see. So let's say we had a one-tailed test and we were looking to increase happiness, right? So if we were doing a behavioral exercise to increase happiness, we only wanted to increase happiness, right? So if it's a one-tailed test, the critical value, if you look here, is plus 1.73, right? So plus 1.73. Whereas the same scenario, if that were a two-tailed test, assuming that the alpha is the same, right, 0.05, two-tailed test, and the number of participants or degrees of freedom is the same, then you're going to get a larger alpha. Now, a two-tailed test allows it to be statistically significant, whether it's on the negative side of the distribution or the positive side. That's its benefit. But notice the critical value is larger, negative 2.101 or positive 2.101. The absolute value of that number is larger than a 1.734. So that demonstrates that two-tailed tests are harder to reject than null because you have to be further on the extreme of the tail. So we talked about a t-test. Now let's talk about an ANOVA or an f-test. So an f-test is also known as an analysis of variance test, or the abbreviation of analysis of variance is ANOVA. And that is a statistical test technically that allows you to determine whether two or more means are statistically significant in terms of their difference from one another. Now, I said if you had two means, the formula is a lot easier to use a t-test. So technically, if you wanted to do an ANOVA for two means, you could, because the f value is always t squared. So you could do it, but most people use the ANOVA for three or more means. Now, you have your systematic differences. These are your mean differences. That's in your numerator. And you have your error variance, which is your error, as we said. So the systematic differences are, or systematic variance, pardon me, is the variability caused by the manipulation. So in this case, we're comparing the difference between the averages from the grand mean. Now, the grand mean is a fancy word for the average of all the averages. So we're comparing in the numerator differences from the grand mean. You might hear that referred to in the graph as between groups variance. Error variance is on the denominator, and that's fluctuation within a specific sample. So that's why it's referred to as within groups variance. That's error. Now, we also want to calculate effect size and confidence intervals. That's meaningful. So when you calculate effect size, that is the relative impact of one variable on a given outcome. How much of an impact did your manipulation have? Confidence intervals have what to do with generalizability to the from the sample to the population and so forth. Now, we have a decision to accept the null or reject the null. Remember, we talked about the null hypothesis saying no differences between the groups. The alternative or research hypothesis said there are differences between the groups. As a researcher, our goal is to reject the null hypothesis, but sometimes we make the wrong decision. Now, a type 1 error is when you make a mistake and you reject the null, saying that there are statistically significant differences between the groups when there really weren't. So a type 1 error is when you reject the null when you should have accepted the null, right? And that happens when you have a large t-value or f value, because the probability of this occurring by chance is relatively small. Now, we also have a type 2 error. A type 2 error is when you accept the null when you should have rejected it. Now, accepting the null means that you said there are no statistically significant differences between the groups, when in reality there were. And the question I have for you to think about is whether a type 1 error or a type 2 error is worse. Well, let me give you an example when a type 1 error would be worse. If you were to prematurely put out a coronavirus vaccine and say, this coronavirus vaccine works, It's effective because in my research studies, I found significant changes in probability of getting COVID. That would be a type 1 error if people still got COVID. In that case, that's going to be a problem. Whereas a type 2 error, that's going to be worse with things like cancer or things like missile control. So if you're a radiologist and your job is to detect masses in the body, and you do your imaging and you say there's no mass in the body and it really was, well, that could be fatal. That's a type 2 error. And the same thing could be said in missile control. Imagine you're on the southern border of the United States and you're tracking missiles coming in, and you're sitting there looking at your computer screen and you have a blip on the screen and you're not sure whether that blip is a missile or whether it's nothing. Well, if you say it's nothing and it turns out to be a missile, there are going to be a lot of casualties. Whereas if you say, oh, I think I see something, and you go into, I don't know, some emergency procedure, and it turns out to be nothing later, people might make fun of you. They might call you the boy who cried wolf, but at least there are no fatalities. So a type 2 error is when you say there's nothing doing, no real differences between the groups, when there are. So there is a scenario when a type 1 error is worse than a type 2. There is a scenario when a type 2 error is worse than a type 1. But most of our research studies do not deal with life or death consequences. So we generally say a type 1 error is actually worse than a type 2 because you might mislead scientists in believing there's some meaningful outcome. And then things like the alpha is going to play a role in a type 2 error and a type 1 error. So the smaller the alpha, the larger the type 2 error. The smaller the sample size, the larger you're going to make a type 2 error. The smaller the effect size, the more you're going to make a type 2 error. Now, here's a scenario. Here's just a Punnett square where you can make the right decision or the wrong decision. And as I said, there are 2 wrong decisions. If you are a forensic psychologist or you are a juror, better yet, on a forensic case, and you had to determine whether a person was innocent or guilty, what happens if you find them guilty, but they were actually innocent? So that would be an example of a type 1 error. So they're wrongfully convicted. A type 2 error would be when you find them innocent when they're actually guilty, right? So that's what it would be. Now, choosing your alpha, as I mentioned, your standard alpha is 0.05. If you have more than 2 groups, you might consider a 0.01 alpha. But generally, as I said, a type 1 error is considered more serious than a type 2 error because you might mislead scientists. So power, the goal is to accurately reject the null. When we say you have statistical power, that's the strength of your ability to accurately reject the null. And that is 1 minus the probability of making a type 2 error. Now, every study, if you want to make sure that you have meaningful outcomes, you never want to attach too much emphasis to one outcome. So most researchers encourage replications, which is to redo the study and see if you get similar outcomes. Because the more you redo the study and you get similar outcomes, the more confidence that you have in that outcome. So you definitely want to, in your method section, provide enough detail that someone could redo your study and see if they get the same or similar outcomes. There's actually a vaccine now that they had a methodological flaw. and I guess it's the Oxford vaccine. And now, granted, it worked. So the vaccine doesn't pose an increased threat to the public, but when they reported that their vaccine was effective, they said it was effective up to 90%, and then in one scenario it was only 63% effective, and it was because they gave a half a dose versus 2 full doses, and that methodological flaw screwed up their outcome. So what are they doing? They're actually, before they release this vaccine, they're doing another phase 3 trial to make sure that their vaccine is truly effective before it goes to marketplace. So replications are important for consumer safety and for our confidence as researchers. Now, if you want to run a statistical analysis, there are many software programs that one might find. You could do it in SPSS, you could do it in SAS, you could do it in Minitab, you could do it in Excel. All of these are at your disposal. There are other programs like R and so forth, really fancy statistical programs. But in psychology, most of us use SPSS. And there are 3 phases. You have to do data entry, data analysis, and then you have to interpret the output, right? So there are 3 phases. No matter what statistical program you use, you go through these phases. Now, the next decision is based on deciding the right statistical tests. Now, you may recall in the previous lesson, we talked about the scales of measurement: nominal, ordinal, interval, and ratio. Nominal was categorical differences, ordinal was rank order differences, interval and ratio were mean differences. So if you had one independent variable and it had 2 groups, 2 levels, if you had nominal data, the correct inferential statistic would be a chi-square. If you had ordinal data, it depends whether it's repeated measures or independent groups design. Now, you may recall in the previous lecture, I said ordinal data is a little wonky. We won't always have a statistical test, or it's more complicated than the rest. So with ordinal data, you would use the Mann-Whitney U test for independent groups design and the Wilcoxon T test for repeated measures for ordinal data. For interval and ratio data, you would use independent sample T tests. Now, if you have one independent variable, 3 or more groups, nominal data, still chi-square. Ordinal data, notice again, we have to, all these complications. Is it independent groups? Is it repeated measures? Because ordinal data, if you have one independent variable with 3 groups and it's independent groups design, you're going to use the Kruskal-Wallace. Whereas repeated measures, you're going to use the Friedman's T. If you have interval or ratio data, you're going to use the one-way ANOVA. Now, if you have 2 or more independent variables, once again, nominal data, chi-square. Ordinal data, we got a problem. There's no appropriate statistical tests available when you have factorial designs that are ordinal data. So try and avoid ordinal data. Interval and ratio data, we would use a 2-way analysis of variance, or what we refer to as a factorial ANOVA. And that is our lecture for today. I'm going to stop there.